All righty. So going over the properties of alkanes and what we use them for, and then I'll do the same for the other groups that I talked about last week. So the trends in the properties of the alkanes can be explained by looking at their structure. The first and most obvious property is going to be that they are nonpolar because the carbon-hydrogen bonds are nonpolar. So the only forces of attraction are going to be the London dispersion forces. Now, just to review, in case we forgot, London dispersion forces or London forces are basically the result of electrons that are orbiting around the nucleus. And so that at any one point, there might be a higher concentration of electrons on one side of the atom, which is going to make that atom for that particular time slightly negative. And then that's going to create what's called a dipole. A dipole is a very, very temporary charged atom. It's kind of like when we talk about water being polar, but it's very temporary, like I said. And all atoms, even 100% nonpolar compounds like oxygen gas or even the noble gases experience London forces. They're the weakest of the intermolecular forces, by the way. However, the strength of these weak forces is going to increase as the mass of the molecule increases, which makes sense because the more atoms you have, the more possibility you have of spontaneous dipoles forming. And so you'll have more of these very weak forces, which makes the overall force a bit stronger, which means as alkanes increase in molecular mass, then their density is going to increase. So some of the very simple ones like methane, ethane, propane are going to be gas at room temperature. And as you add more carbons and hydrogens, then you have liquids like octane, which is jet fuel, basically. So we have the properties over here. Of course, first property is that they're nonpolar, which you can see all of these carbon-hydrogen bonds, they're all nonpolar. The lowest molecular mass are gases. The highest ones with the highest molecular mass, those are going to be solids. And of course, the ones in the middle are going to be liquids. And as molecular mass increases, so does boiling point, which also makes sense because if these with the lower masses are already gases, that means automatically they're gases because their boiling points are lower. And alkanes are not very reactive. So like I said, everything up to and including butane are gases. If you ever do anything about fossil fuels or energy, things like that, we sometimes refer to something called natural gas. Natural gas is something that obviously is natural. It's like it's produced by the earth. And this is a fossil fuel that we can mine. And it's made of all the alkanes that are between 1 and 4 carbon atoms. So methane, ethane, propane, and butane. These make up natural gas. So that kind of goes behind the picture, but anyway. Right, so because they only have a low number of carbon atoms, that means that they're not going to have a lot of overall total atoms. And so those London forces are going to be quite weak. They don't have a strong intermolecular force holding it together in a liquid or a solid state. Blech, it's hard to talk today. Some of the larger alkanes are going to be liquid. Again, just as you increase the number of atoms that are in the molecule, you're going to increase the mass and then therefore increase the density, which then makes it become liquid or solid. So gasoline and kerosene, these are all kerosene lamps like they used to use in the old days before electricity. There's basically kerosene oil here in the bottom. And then there is a cotton, like a flat cotton ribbon that kind of like the alcohol lamps. I mean, you know how an alcohol lamp works, but in this case, you see the little knob there on the side allows you to twist it, and then the twisting it pulls up more of the ribbon so that you can have a higher flame, which means a brighter light. My parents used to have a couple of these. So the London forces are stronger, mostly, well, not mostly, only because there's just more atoms present in the compound. Alkanes with a very high molecular mass are solid. So here what you're looking at is paraffin wax. I don't know if you've ever done this. I did it once here in Thailand, and it hurts.
Yes. Yes.
Yeah, it does make your skin really soft, but man, when they put that first dip,
It's
I'm like,
hot.
yeah, oh my God, it's so hot. But after that, because they dip it a
Yeah.
few times, I think like 3-4 times maybe, and then they wrap cling wrap around it, let you sit there for like, I don't know, 20-30 minutes, something like that. But yeah, skin's super smooth afterwards. But anyway, that's called paraffin wax, and that is a solid alkane, which you see here, just regular candle wax, unless it's beeswax or soy. Okay, now with increasing molecular mass, you get increase in boiling points. And again, it makes sense because if you're increasing mass and you go from gas to liquid to solid, obviously that is because the boiling points are changing. Just again, because they're just much bigger molecules. And with bigger molecules, you have more London forces. And so it requires more energy to break up those intermolecular forces. Now, the reason why this is super important and how we can apply this to everyday life, because I do try to relate as much as I can and when I can remember to relate what I teach you to like, why should we give a crap? This entire topic, I guess, of the boiling points of alkane is exactly how we take crude oil, which we mine either from under the ocean or from underground, and we separate all of the many different products that we get from crude oil. And that's all based on boiling point. So petroleum or crude oil is the same thing, that really thick black gunk that we take out of the earth. It has a very complex mixture of different hydrocarbons. And of course, when you have something like this, when a tanker hits something, and like an oil tanker, and then a bunch of oil is dumped into the ocean, there are, I don't know how many carcinogens in petroleum. It's really, really nasty stuff. You don't ever want to touch it with your bare hands ever. And then unfortunately, we have a lot of like environmental wildlife damage when this happens. Oh, there she is. Okay. Oops, there we go. Okay, so the hydrocarbon molecules in petroleum contain anywhere from 1 to more than 50 carbon atoms. So all of the hydrocarbon molecules going from 1 to 50 carbon atoms, all of them combined form petroleum or crude oil. This range allows the separation of petroleum with different boiling point ranges. So here we see gasoline. Gasoline even itself is made of different hydrocarbon compounds from 4 to 12 carbons, and the boiling range is up to 200 degrees. Then we have kerosene, which was used in the old-fashioned lamps. Those are from between 10 to 14 carbons, and you see the boiling points slightly below, but mostly above. So you could bring, if you had a mixture of gasoline and kerosene together, you could bring that mixture up to, say, like 250 degrees. And then that would mean that the gasoline will boil, but the kerosene won't. And then you can siphon off the gasoline gas, and then you can condense it later and then separate them that way. Then you've got, I don't know what middle distillate is, but it says heating oil, gas turbine fuel, and diesel. Of course, we should all be familiar with diesel as far as car fuel goes. Those are between 12 and 20 carbons, and the boiling point between 185 and 345. And then you've got wide cut gas oil, such as lubricating oil and wax, between 20 and 36. And of course, again, as you increase mass, you increase boiling point. And then asphalt, who would have thought that asphalt comes from petroleum, but asphalt is made of hydrocarbons above 36 carbons. And when it says residues, that means that it doesn't matter how high the temperature is. I'm sure there's a certain point, but basically in this process, it's going to be left over. You're going to get residue. So that means it's going to be left over after everything else is boiled off and separated. What you're left with will be asphalt. So this process is called fractional distillation. So distillation is basically a separation technique, a physical separation technique where you have a mixture of two liquids that have different boiling points. So again, you use the boiling point to your advantage so that one liquid boils off and becomes a gas, and then you condense that gas, leaving your two liquids separate. The reason why they call it fractional distillation is you have many different products, not just two. And so it's still a type of distillation where you're using boiling point in order to evaporate one of the component parts into a gas, and then you'll condense it later in what's called a fractional or fractionating column. So the petroleum is heated to about 370. And that means nearly all the parts of the petroleum are vaporized, of course, except for the residue, which makes up asphalt. As that vapor rises, they gradually cool down. Now, alkanes that have a higher boiling point are going to have higher condensation temperatures. So remember that boiling and condensation are two opposite processes, like either from liquid to gas, or condensation is gas to liquid. So they're going to occur at the same temperature. So as they start to cool, the heaviest hydrocarbons are going to condense first. And so they're going to be collected lower in the tower. So you can see the lubricating oil stocks are at the bottom. Those are the heaviest. Then you've got gas and oil, kerosene, and gasoline. Alkanes are less reactive than the other hydrocarbons because of the stability of these single covalent bonds. So one reaction that they do go through, however, is combustion. And the most important reaction is with fuel. Complete combustion. Here's the thing. If you completely combust an alkane, the only byproducts are energy, carbon dioxide, and water. The problem is the way that we engineer engines is that it's not complete combustion. So that's when you get byproducts. When the fuel ignites spontaneously before it reaches the flame, there is a decrease in the amount of power gained, and you get something called engine knocking. I don't know if you talk about this in physics, if you talk about combustion engines at all, but basically, if you get certain types of fuel close enough to a flame, it will spontaneously ignite before it actually touches the flame. Therefore, it ignites, and it's going to cause, I think it's the pistons. I'm not a mechanic, so I don't really know the ins and outs exactly, but I think it causes pistons to misfire, and you like literally hear your engine knocking, like a duck, 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 duck kind of sound. Now, what causes this is the type of hydrocarbon that's in your fuel. So straight chain hydrocarbons are more likely to ignite spontaneously than branched chains. So this is the basis of rating with the octane scale. And the octane scale is what you see at the gas station, where you can choose between either, what do they have here, 91, 95. Although a lot of it is being converted to like gasohol and stuff like that, but that's anyway. So the octane rating is a fuel's burning efficiency. The higher the number, the better quality the gasoline is. And these are based on a mixture of two alkanes. You've got heptane, which you know what that is now. Heptane, which is the straight chain made of 7 carbons. And the other alkane they mix in with that is 2,2,4-trimethylpentane. That's highly branched. Obviously, you have a smaller 5-carbon. So just write that out. So your heptane, 1, 2, 3, 4, 5, 6, 7, and your pentane, 1, 2, 3, 4, 5, and 2, 2, 4. So 2, 2, 3, 4. So depending on the percentages of each of these, you get the octane scale like this. So I don't even know if any gas stations sell 87 anymore, but in general, you have 91. I think in the States you've got 93, and of course here you have 95 as well. 95 would be the highest rating. So the term octane comes from the common name of 2,2,4-trimethylpentane, which is called isooctane. And they call it isooctane because it has 3 methyl groups and the parent is 5. And so it's an isomer of octane. Pure isooctane, so that would be, you would have an octane rating of 100%, which of course we don't. Our highest here is 95. You would have only 2,2,4-trimethylpentane, and that's very resistant to knocking. And so the more heptane you add, then the lower the percentage gets. So isooctane 100% is given an octane number of 100. Oops, I don't know what's behind that, but never mind. Right, okay. So those are the properties and uses of alkanes. Let's go to alkenes. Again, alkenes are nonpolar because we're not talking about functional groups yet. So all of these compounds are nonpolar. The boiling points physical states are going to be very similar to alkanes. So again, here we have they're nonpolar. Lowest molecular mass or gas, highest molecular gas or solid, and boiling points increase with increased molecular weight. Now we've got here pure lemon extract, which is limonene, also called oil of lemon, is an alkene. You can see the structure there. So this is weird because you actually have a carbon ring. I don't even know. Yeah, I don't know what the technical name of that would be because how would you go? I don't know. I don't know what that is. I don't know what the technical name of that would be, but we call it limonene. All right, alpha farnesene has 15 carbon atoms and 4 double bonds. It is a solid at room temperature and atmospheric pressure, and it is found in the natural wax coating of apples. You ever buy apples and they have this kind of dull, waxy appearance? That is from this alkene, which is completely natural. And this is what it looks like. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, oh, I forgot to look up 11. 12 is dodeca. So that would be dodec. And then 1, 2, 3, 4. Dodecatetraene, I guess. And then you have to number it. So it'd be like, that's 1, 2, 3, 4, 5, 6, 7, 9, 10. So 1, comma, 3, comma, 6, comma, 10 dash. And then we've got methyl, methyl, methyl. So trimethyl. And that's on 3, 7, and 11. So the technical name, if I did this correctly, the technical name would be 3, 7, 11 trimethyl 1, 3, 6, 10 dodecatetraene. Yeah, see, directions. Anyway, that's apple wax. Alkene. Ethene is a hydrocarbon that's commercially made in the greatest quantity in the United States. It is used in the synthesis of plastics, and it is commercially important alcohols and in commercially important alcohols. This is the plant hormone that I talked about last year when I mentioned one bad apple spoils the bunch. I can hear my dog, whatever, I'm going to ignore him. Ethene causes fruit to start ripening, but if it's produced in, say, like a great quantity in fruit that's being transported, a lot of times it can cause rotting. And as soon as it's starting to be released, it causes the rest of the fruit to also release it. Okay. And then alkynes, again, nonpolar. The same trends in boiling points and physical states. In welding torches, they mix ethine with pure oxygen. Oh, okay, fine. He's whining. Give me a second. You happy now? He's better now. All right, so welding torches, when you want to put two pieces of metal together, then that's ethine. And of course, ethine is two carbon atoms with a triple bond between them. Okay, same thing. And the last group are the aromatic hydrocarbons. There we go. Okay, and aromatic hydrocarbons, of course, are when your parent molecule is the benzene ring. The benzene ring is very stable. It is less reactive than alkenes and alkynes. In the past, benzene was used as a nonpolar solvent, basically a substance that you could clean like oil and like wax and things like that when you want to clean those things, because they would dissolve in benzene because they are polar and benzene's non-polar. Sorry, did I say polar? They are nonpolar and benzene is nonpolar. But now, of course, we realize, oops, it's poison and it causes cancer. So let's not use that anymore. When the body tries to eliminate it by oxidizing it, it produces toxic molecules. So we stopped using that. I think we use toluene now, which is also not great, but there's, what do you call that? An aromatic hydrocarbon called 3,4-benzpyrene that's found in coal tar, tar from cigarette smoke, and soot in heavily polluted cities like Bangkok. Studies show that this too causes cancer. So we have chemical stability, less reactive than alkenes and alkynes, and nonpolar. So this is probably one of the most well-known uses of a benzene derivative, and that's naphthalene. Naphthalene has a very, very specific smell. And if you know what this smells like, it's something that you don't forget very easily. But naphthalene is two benzene rings that are fused together, which you can see there in the diagram, and it's used as a moth repellent. So if you have mothballs in your closet, or sometimes they make them into like little cakes, I guess. I don't know if urinal cakes are made out of the same thing, but basically these are the things you put in your closet so that moths don't eat your clothes. It has a very, very, very particular odor to it. Okay, I think, yep, that's it for proper